Hello, this is John Perham here, and I'm going to present the solutions of last week's test problems for the course MATH1231. And there were two problem sets, so we'll do each one of them. So the first set is going to be the buff or brown questions, and so we'll start with the first problem. So we can take this matrix here, A, define its rows, and we can view it as a matrix using this. And the questions are: find, giving reasons, the rank of this matrix and its nullity, and find a basis for the image of A. Well, the way we do these is to carry out row reduction on the matrix. So what we need to do is to add twice the first row to the second and 6 times the first row to the third, and we can do that using that and view the result using that. And we can see we've got zeros here down the first column, and now we do the second phase. So we want to subtract 13 times this row from the third row, so we can do that using that and view it using that, and we can see we've got a row of zeros in the bottom here. So so this matrix has only two leading columns, namely the first one here and the second one, and so its rank is 2, and thus by the rank nullity theorem its nullity is 1, because these should add up to the number of columns. And a basis for the image of A is therefore provided by the two vectors, which are the first two columns of the original matrix A. And we can drag those out and view them as a column matrix using this. And we've got to execute this up the top here, so we'll go back and do that. And now come back and do it again. And there they are. So that's the basis for the image. Now we go on to question 2, and we've got another matrix A, whose rows can be entered using that, and which can be viewed as a matrix using that. And we want to find the eigenvalues and eigenvectors of this matrix. Well, that's a fairly standard kind of thing. So what we do is we form the matrix B, which is lambda times the identity matrix minus the original matrix, which we can view looking at that. And there it is there. And now we form the characteristic polynomial, which is the determinant of this matrix, because the eigenvalues are the zeros of the characteristic polynomial. So let's work out that's a quadratic equation, so let's work out the discriminant, and that's 49, and that's positive, so the eigenvalues will be real and distinct, and we can use the formula for a quadratic, the solution or the zeros of a quadratic polynomial to find the eigenvalues, and they are 3 and minus 4, and they are indeed distinct. So let's get at the eigenvectors. So here's the first eigenvector. Well, here's a general expression for an eigenvector, and we can find the equation this satisfies by multiplying that vector here by the matrix B evaluated at the first eigenvalue, sorry. And there it is, and we can see that this first equation here is the negative of this one, so that looks good. And so we can find the components of the eigenvector by setting the first one equal to 0, solving for y, and then setting x equals 1, since the eigenvalue or an eigenvector is still an eigenvector when it's multiplied by any scalar. So we do that using this, and there's the value of y, and we better check that that is a solution of the second equation and see that it is, so we can work out the first eigenvector. It's that. Which we can visualize. So I'll put that in. Can be visualized as a column matrix using that function we defined above. There. We'll need that for the second eigenvector, so we'll just copy that. Okay, now we move on to the second eigenvector. So we do the same thing except for the second eigenvalue. So we take the product of the matrix B times that vector and evaluate it at the second eigenvalue using that, and we can see that this equation here is minus 9 over 2 times this one. So that's good. In other words, they're linearly dependent. So we set the first equation equal to 0 and solve it for y and set x equals 1. And we better check that that's a solution to the second equation, and indeed it is. So the second eigenvector can be found using that, and we'd like to visualize it. So we copy that down and customize it a little bit, and that's the second eigenvector. So we've found that, and now we go on to the third problem. So this is about probability. So we've got a discrete random variable x, and it has a probability distribution given by this. So the kth element of this distribution is c times k. And that's for k equals 2, 3, 4, 5, and we're asked to find the value of the constant c and to calculate the expectation value. Well, we can see that all these elements here, provided c is positive, will be not positive. So that's the first condition, and the second condition is that all these guys here sum up to be 1. So we sum all the elements from k equals 2 to k equals 5 using this. And we must have forgotten to execute something here. We did. So this assigns to the variable pk the actual value c times k. So now we do that again, and that's 14c. And of course, if this is to be a probability distribution, then this sum must be 1. So we get an equation for c by setting the sum equal to 1 or minus 1, and then we can solve for c by setting that equal to 0 and solving the linear equation, and we get 1 over 14. And now to calculate the expectation value, or the mean, then the mean is given by k times the probability distribution, and we have to evaluate that for the value of c, and the answer comes out to be 27 over 7. So they were the buff problems, and now we want to go to the blue problems. The first question was, we have a matrix A, which we can establish using that, and view it as a matrix using that, and we're asked to giving reasons to find the rank of this matrix and its nullity, and then in the second part we've defined a basis for the kernel of this matrix. So again we proceed by row reduction. So we want to get zeros here and here, so we add twice the first row to the second and 3 times the first row to the third, and we can do that using this, and then we can view it as a matrix using that, and we can see that we have indeed got zeros down here. And now we want to do the second phase, so we want to subtract twice the second row from the third row, and we can do that using this here, and there we go, and we can view it in a matrix form using that. And we can see that there are only 3 leading columns here. See, there, that's a leading column. That is, this one isn't, and this one is. So since there are 3 leading columns, the rank of the matrix is 3, and thus by the rank nullity theorem, the nullity is 1. So we now need to find the kernel, or the, so we'll let X be a vector with components we can establish using this, be in the kernel of A. That means, well, what does that mean? Well, it means that it has to be a solution of AX equals 0. Well, we've now done rate reduction, so the equation corresponding to the third row, we just have to extract that. So that equation is this, and that has to be 0, so that means that x4 must be 0, so we can indeed set that equal to 0 and solve it for the fourth variable, which must be 0. And now we come to the second row of this equation, and so that equation can be formed, or the left-hand side of it is this, so we can set that equal to 0, which is the right-hand side, and solve for the second component, and that will give us x2 as minus 4x3. And then we do the same thing with the first row, so we take the first row, take its scalar product with the vector of variables, and apply the solutions we've found, and that will give us an equation which is a connection between x1 and x3, so we can set that equal to 0 and solve for the first variable x1 using that. And now so we found a vector in the kernel of A, and there it is there, and that will be a vector for any value of x3, so we set x3 equals 1, and there's the solution. So that's a vector in the kernel of A, or if you like, it's a basis for the kernel. And now we go to question 2, and that's much the same as question 2 in the first lot, except the matrix is different. The matrix can be established using that and visualized using that. So we do the same thing. We form the matrix B, which is lambda times the identity matrix minus the matrix. There it is. And we can visualize that matrix using thus. and the eigenvalues are the zeros of the characteristic polynomial, which is the determinant of this guy here, and we get that out there, and that's a quadratic equation for lambda, and we'll calculate its discriminant to see what kind of solutions we can expect, and this is negative, so that means that the eigenvalues in this case will be complex, and they can be found using this. So they're the eigenvalues of this problem, and you can see that they are complex conjugates. We weren't asked to find the eigenvectors, so we won't do that. Just have a sip of coffee and I'll be back to you. So now we move on to question 3, and this is not the solution, this is the problem. So we'll just correct that. So we've got a matrix A, which we can establish using that, and view as a matrix using that, and we're told that it has its first eigenvalue is -1, and its second one is 2, 3, and its first eigenvector is 2, 3, and the second eigenvalue is 9, and the second eigenvector is this one here. And we're asked to write down the general solution of this system of differential equations. Well, let's define the solution as this vector valued function of t, and if we multiply this vector here by the matrix, we can see that this is the same as the right-hand sides of these differential equations. So in other words, this dynamical system is of the form, the derivative of this vector is equal to a times y, and the solution of that problem, which is this vector here, is given by a constant, alpha times the first eigenvector times e to the first eigenvalue times t, and then plus beta, the second constant, times the second eigenvector times e to the second eigenvalue times t. So that's the general solution to that problem. And now we come to the fourth question, and that is show that the sequence defined using this, so the value of pk is k over 75 for k equals 3 up to 12, is a probability distribution. Well, we can see that the elements of this distribution are all positive, so that's the first condition, and to see whether it's a probability distribution, we have to sum the elements of the sequence to check that they're actually equal to 1. So we do that here, and we've got to do this. So now we do it again, and that is indeed 1. So this is indeed a probability distribution. Now, of course, to actually calculate these things here, there's a fair amount of arithmetic. But anyway, the principle's okay. So let's stop there, and